All right. So I hope that the screen is perfectly visible to everyone. Yeah. Yeah. Audio is also fine. I think so. Yeah. A very, very good afternoon or good morning or good night, whatever time it is for you guys. For me, it's afternoon. So now let's move on to our discussion further. Okay. Now we were discussing about the MI of a thin rod, right? Okay. So let's continue with that. And so far we have done the MI of this rod about the central axis through one end. And now let's make the axis inclined. Fine. Okay. So let's take that up. And this is an important it's an important derivation. Result also. Fine. So moment of inertia of a rod at an inclined axis. Let's do that. Inclined axis MI. We're going to do this for a rod. For other cases also you can do. It would be slightly difficult. Fine. Okay. So now let's take up the case. And this is the center of mass, and we are going to set this as the origin itself, x equal to 0. This one over here is the axis. Fine. And the axis is not at 90 degrees, it is at a theta value over here. Fine. And what we can do to find the moment of inertia about this axis. Again, element. Mass of the element, dm. Distance of the element from x equal to 0. We are going to take this axis as the x-axis. And therefore, this distance over here is how much? X. What is a small increase in this x value? Dx. Fine. So, therefore, now, what do we want next? The small amount of moment of inertia, right? Elemental mi. So, what's the elemental mi? Di is nothing but equal to dm multiplied by the square of the distance from the axis. But the axis is not this way, right? So the distance from the axis is actually going to be this particular distance over here. Okay. This one. Now, how much is this particular distance from that axis? We notice that the hypotenuse over here is nothing but x, right? For this triangle, this one. So therefore, the component of x in this direction would be which component? X cos theta would be this one. X sine theta would be this one, and that's all. So therefore, over here we can write that this is nothing but equal to x sine of theta. Fine. So therefore, let's substitute that over here. X sine of theta. Now, is theta a variable quantity? No, unfortunately, it's a constant. Whether you select whichever element, the axis is still going to be inclined this way to the rod. Fine. At the same angle. Integrate over here. What do you get? You can take the sine square theta outside, and it would be dm into x square. And what would be dm? Lambda dx times x square times sine square of theta. What would be the limits of integration? The lowest possible value of x to the highest possible value. That means from minus L by 2 to plus L by 2. Fine. Substitute that over here. What do you get? Is it the same as the first derivation on the rod that we did? Except there is a sine square term. Yes, yes, yes. If you go back to the first derivation that we did, this one. Lambda dx x square, find minus L by 2 to plus L by 2. The only addition is Here there is an additional which term? Sine square term. That's all. So you just write sine square additionally. Fine. That's all. Our proof is done. Fine. So therefore we directly write it as 1 by 12 ml square into sine square theta. Fine. You can verify this by setting the value of theta as how much? How do you check this over here? Set the value of theta as 90 degrees. Axis has to become 90 degrees, right? And it will come out as 1 by 12 ml square. Fine. And you notice one important thing, that if you were to set the value of theta as 0 degrees, you actually get I value of 0. Why is that? Why is that? Because you remember the principle behind this rod is that the idea behind it is that this is a very, very thin rod. So all these particles, they lie on this line itself. That means they don't have any distance from this particular line. This is for a theta value of 0 degrees. So mass into distance square is actually mass into 0 square. Fine. And you can also go for the mi about an axis passing through one end and inclined at theta. Fine. The same proof you can do also. Here we'll just make a side note. Fine. That this is the axis, and actually, sorry, this is a rod, and this is the axis over here. This angle is theta. You can set the x value as 0. We want to find out the value of mi for this one. You can take an element over here of dm mass and distance. What? अरे रुक जा रे, मैं तेरे लिए रिकॉर्ड कर रहा हूँ. रुक जा. You interrupted the record actually. मालूम है? Yeah, I was recording right now. It's for you only. No, keep the call. Call रखो. Extremely sorry for that, guys. Hmm. Hold on. So, what what were we discussing right now? Someone called just now. Extremely sorry for that. Fine. So this distance over here is how much? This is x, and this is nothing but how much? Dx. Fine. And what can we say for this one? What do you say? 45. I lost my train of thought. So yeah, so you take the distance over here. Yeah, this is the distance, right? Okay. And therefore you get x sine of theta. And what is your di? This is nothing but dm into x sine of theta the whole square. Limits would be from 0 value to L value. And once you do this integration, and I want you to do this by, yeah, I want you to do this because you guys are now my students. Yeah, I do. So the dm is lambda dx. You substitute this over here and put the lambda as finally m by L. You should get it as 1 by 3 ml square sine square theta. Fine. Fine. All right. Just take a break over here. We'll continue this in the next lecture. Fine. Yeah, this is short videos. We'll keep it that way. Fine. All right. I'll see you guys. Bye.